All right, 11.5, partial fraction decomposition. All right, so for this section, I feel sorry for some of my online students because they watch some of the videos from the textbook. And of course, it's 100% legitimate and correct. It's just told to you in a real mathy way. Okay, here are the formulas, here's this, and this. The way I teach it here is pretty much the same thing, except I don't give you all the crazy notation. P of x over q of x is equal to a1 over x minus a sub 1 plus a2 over x minus a sub 2 plus all the way down to a sub n all over x minus a sub n. Yeah, that you had no idea what I just said, right? So what we're going to do is just look at what we have, figure out how it matches one of the particular patterns that we are trying to decompose this fraction. Okay, so we've got a couple of scenarios. So we're going to look first off, what is partial fraction decomposition? So if I say something like, let's say, easy fraction. Let's say 5/8. Okay. Simple. Give me two fractions that add up to 5/8, but with different denominators, not in eighths. So like uncommon denominators. So how about so let's just think about what the denominators would be. 4 and a 8 will work. That's a common denominator. 4 and 8 is a common denominator of 8, right? So I could say there's some number, let's call it a, and some number b here. To where if I would make everything multiplied by 8, I'll clear out this equation, right? So I would have 5 is equal to, this would be a 2a, and this would be a 1b, right? So something like that. So I need to figure out a and b, possible values of a and b that can give me 5, right? So a, if I say a could be equal to, say 2, then b could be equal to just 1, right? That would work. That would hold true for that. Yeah, like I'm trying to just clear out all my fractions. So divide, multiply everything by 8. So 4 goes into 8 2 times, 8, like that. So it basically simplifies down to where I'm not working with fractions anymore. I can just figure out what my numerators are going to be. So that's one scenario. You can also do, say, maybe a could be, what if I say 3? That's 6. Then I have to say -1, right? So b would be a -1. So there's a bunch of scenarios for this particular situation, right? But this is the same concept that we're going to do. We're going to take the fraction that we have, and we can factor it in many different ways, but we're going to take the easiest factorization and make that our denominators of our other fractions. And then we'll find a common denominator, clear out the fractions just like I did, work with the numerators. Okay, so you'll see a pattern emerge from all the different cases. And so you don't really have to memorize the cases. We have 4 of them, but I'll write them out and you can refer back to them. So case 1 is we have a p over x, p of x over q of x is equal to some blah, blah, blah rational function, right? Where q has only non-repeated linear factors. All right, so example. Let's say decompose You know why they name it this. Decompose. It's like when you think decompose, the body's rotten, right? All right, 4 over x squared minus x. So the first thing we want to do is factor it. Always factor it, because that's going to help you determine your denominator's factors in the other two fractions or three fractions, four fractions, however many we're going to have. So first factor. So this will be 4 over, I could take out an x, right? X times x minus 1. Okay, so each factor is linear, right? X to the first power and then x minus 1, x is still to the first power. So take note of how many factors you have. This is going to equal the number of fractions. So we got two factors there. They're both different. They don't repeat, right? They're linear. So I'm going to rewrite 4 over x minus 1 is equal to two fractions added together. And I want the two fractions denominators over here to form the least common denominator that is right here. So I take an x and an x minus 1. The product of those two is common denominator, right? That's always the case. Maybe not the least common one sometimes, but it is a common denominator. So now I say there is going to be some expression here, some here for my numerators. So I just call them A and B, make it easy. So next step is to multiply both sides like we just did with the simple 5/8 problem. By the LCD. In this case, our LCD is x times x minus 1. All right, so I have x times x minus 1 multiplied to the 4 times the x minus 1, x times x minus 1. This, all your fractions denominators should clear out. Shouldn't have any denominators left over. Step 3. Simplify. So we'll have how that cancels out, leaving a 4 on the left. That x cancels, leaving that a times x minus 1. And the b multiplied to just the x, right? And distribute everything across. Ax minus 1a plus bx. All right, step 4. We're going to equate the like coefficients of like powers of x. So all the x to the first powers on the left have to total the x to the first powers on the right. The x squares, same equals the total of the x squares on the right. So we're going to start off with the highest power that we see in there is x to the first power, right? So left side and right side. All right, so we say x to the first power. What do we have? How many x to the first powers do we have on the left? none, right? We have a constant. So that's 0 is equal to the total of the x's on the right side. So a and b's are coefficients, right? So how many x's do we have? Or how many x's do we have? 8 of them, right? If the a was a 5, it means we have 5 of them. If we have 10 of them, 10 of them. So this is equal to 0 is equal to 1 second. Oh, and the b. I forgot the b right there. We got a x's and b x's, right? So a plus b. There you are. Then we go to x to the 0. X to the 0 power, it is in there. Anything to the 0 power is 1. So these are your constants, really. You don't see your x to the 0s. So on the left side, we have a constant of a 4. On the right side, notice there is no coefficient, no variable on this a coefficient. So that's a constant right there. A is a number, numerical value. So that's negative a right there. All right, so this is an equation, 2 equations with 2 variables, right? So 2 equations with 2 variables is a system of equations. Solve the system, step 5. All right, so obviously 4 equals negative a, therefore a is negative 4, right? So sometimes they're very easy to solve just by hand. A lot of times the coefficients are really easy to determine. So if a is negative 4, the top equation I could substitute 0 is equal to a plus b. Means 0 is equal to negative 4 plus b. Therefore, b is equal to positive 4, right? So there we go. That's your a and your b values. That's your numerators of those 2 fractions with the previous denominators. So step 6, there's only 86 steps. That was the last step. Rewrite the given fraction in its decomposed form. So we started off with, I have to go back and look and see what it was. Forgot. Four over x squared minus x. Is equal to, we had a factor of an x there, and a factor of x minus 1 here. Our a was here, our a is negative 4, and our b over here is positive 4. That's it. So the same process is done no matter for the other cases. Okay, we can still see, I find a common denominator, the number of factors I see there tells me how many fractions I'll have to decompose that given fraction. And then we're going to have to figure out our numerators. Now notice our numerators in this case here. Our denominators are x to the first powers, right? Linear factors. One less than linear is constant. So on the top, we've got constants. We start looking at quadratics in our denominator. One less than quadratic is linear, x to the first powers. So our numerators will be in linear terms. So our numerators will always be 1 degree less than our denominators. Okay, so we'll see those scenarios coming up. Case 2. So we'll go through all 4 cases, and then we'll do a few different examples and just see how you don't necessarily need to memorize the scenarios. Okay, you can just see the picture and you're like, oh, okay, I need to do this. So case 2 is where Q has repeated linear factors. So let's decompose x squared minus 4x plus 12 over x cubed minus 4x squared plus 4x. All right, so our first step was to factor, right? So I'm gonna factor everything, numerator and denominator. Numerator is all not that important because we don't change it too much, but why not do it if it can be factored? Actually, I'm not gonna do anything with the numerator because we're gonna eventually equate the like terms, right? On the left, so we want it all multiplied out, term plus term plus term, right? So I won't even do that. But the denominator needs to be factored to determine how many factors we have and if any are repeated or not. So leaving x squared minus 4x plus 12 in the numerator. Denominator, notice I can take out x, correct? Leaving x squared minus 4x plus 4. And it could continue to factor it, right? So that trinomial is a perfect square trinomial. You get x minus 2 times another x minus 2. Repeated linear factors. All right, so take note of how many factors we have there. 3, right? I can write one of them as x minus 2 all squared, right, if you wanted to do it that way. Still, in this case, you still need to recognize that that is 3 factors, right? 2 factors of x minus 2 and one more factor of x. Inside, they're linear. So if they're linear, on top, their numerators will be constants, okay? How many fractions do I need? 3, right? So I'm gonna have x squared minus 4x plus 12 over x times x minus 2 all squared. It's going to equal 3 fractions whose combination of denominators can form the least common denominator. And all you're doing is looking at the factors. I have one factor of an x. I have a factor of an x minus 2, just to the first power. And then over here, I'll have x minus 2 to the second power. So net multiplication of all 3 of those denominators give you the least common denominator because the second fraction's denominator is also included in the third fraction's denominator, right? So if finding the LCD is the denominator of the given fraction, right? So this is my LCD. You can say x, if I have all these, is x in there? Yes. I go here, x minus 2, is x minus 2 in there? Yes. And if I go to here, x minus 2 all squared, is it in there? Yes. Right. So if you would multiply all 3 of these together, these denominators, you'd end up with 4 factors, right? We don't want 4, we still just want 3. So you take each factor that you see, and if this was, say, to the 5th power, you'd have a lot of fractions, right? You'd have one denominator of x minus 2, one denominator of x minus 2 squared, another one cubed, another one to the 4th, another one to the 5th, right? So you just keep on raising that exponent for each fraction's denominator. All right, so over here, we know we need, these are linear, right? So constants on the top, a, b, and a c. We're going to multiply by the LCD to every one of these. All your denominators need to cancel out. This cancels with that. This x cancels with this x. x minus 2 cancels with one of these x minus 2's. So this square will go down to a 1. X minus 2 squared cancels with x minus 2 all squared. So on the left, we're just left with our numerator. Over here will be a times the x minus 2 all squared. The bx times the x minus 2 to the first. And the c multiplied to just the x. All right, so simplify. X minus 2 all squared. That's a binomial squared would be x squared minus 4x plus 4, right? A gets distributed to that. So that's ax squared minus 4ax's plus 4a. Then bx gets distributed across, so that'll be bx squared minus 2bx's plus cx's. All right, so you start off with the highest exponent, which are squares. So we do left side equals the right side. Equate the coefficients. So right here we have 1 x squares is equal to ax squares and bx squares. So a plus b. Let's see, let's pick green, I guess. Next, x to the first powers. So x to the first powers, we'd have a negative 4 is equal to negative 4a's, negative 2b's, and 1c. So negative 4a minus 2b and plus 1c. All right, then we go to constants. But orange. So our constants, we got 12 is equal to 4a's, and that's it. All right, so we have a system right here. 3 equations, 3 variables, right? So once these systems start getting bigger and bigger, then we might want to do it as a matrix to put it in a calculator. This one's not too bad because look, we can easily solve for a using the third equation, right? So solve 12 is equal to 4a, therefore a is equal to 3. I can go into equation 1. 1 is equal to 3 plus b, so therefore b has to be equal to 1. Not 1, I'm sorry. Negative 4. No, negative 2. Negative 2. Wrong button. All right, so b is negative 2. And then I can use the second equation to solve C. It's the only one that has a C anyway. So negative 4 equals negative 4 times our A, 3, minus 2 times our B, negative 2 plus AC. Negative 12 plus 4 plus C. Negative 8 plus C. Add 8 to both sides, you will get positive 4 for C. All right, so we have go back and rewrite it. We had original x squared minus 4x plus 12 over x cubed minus 4x squared plus 4x is equal to a fraction with the denominator of x, had a on top, a is 3. Next fraction, x minus 2 was b on top of that, so it's a negative 2. And then we had x minus 2 all squared, which is a 4 for C. All right. Case 3. Q contains a non-repeated, irreducible, quadratic factor. Decompose 1 over x cubed minus 8. All right, so we have to factor the denominator. All right, if you're probably not too familiar or haven't had much exposure to factoring sums and differences of perfect cubes. Most time you see it, you don't see it too often. Trinomials are the big ones, right? We always factor trinomials into two binomials. If I have a sum or a difference, let's do a sum of cubes. So if I have x cubed plus, let's put a and b instead. Format of a cubed plus b cubed. This is going to factor as a plus b as a binomial, and then it's going to be multiplied by a trinomial that is quadratic. It'll be a squared plus ab plus b squared. Oops, I'm sorry, this is supposed to be a minus ab in right here. Sum of cubes. Difference of cubes. same format, but if I have a cubed minus b cubed. So like we can factor a difference of squares, right? A squared minus b squared, a difference. That's a plus b times a minus b. Factors really easily. You can't do a sum of squares. There's no such thing to where you FOIL it out, you will get the original back. But this right here, a cubed minus b cubed or a cubed plus b cubed can factor. Same format, this would be a minus b, a squared, then plus ab plus b squared. All right, so this is how you come up with your signs, no matter if it's sum or a difference of cubes. S, O, A, P, SOAP. Same, opposite, always positive. All right, so look at the binomial. It's the cube roots of each term in there, right? Keeping the same sign that you're originally starting with. And then the trinomial is just a matter of squaring the first term, change your sign to the opposite. The next term in the trinomial is the product of these two numbers, a and b. And then the last is just squaring the last. And squaring a negative or a positive always gives a positive anyway. That's why that comes out to be positive for that last term. So if I factor x cubed minus 8, this will be binomial times trinomial. Cube roots of each one of these. Cube root of x cubed is x. Cube root of 8, 2. Same sign. Then I look at this binomial to get the trinomial. Square x, opposite, multiply 2 and x, positive, always positive, 2 squared, 4. All right, so it's totally factored. The trinomial you cannot factor any further, right? So how many factors do you see? It's the same process over again. 2 factors means 2 fractions, right? All right, so I'm gonna have 2 fractions. They don't repeat, so that's nice. So this first fraction is going to be x minus 2. The second one would be the x squared plus 2x plus the 4. The product of those two is the common denominator that's shown. Now I mentioned earlier, your numerators are always 1 degree less than your denominators. So this is x to the first. 1 less is a constant, call it a. Over here, 1 less than quadratic is linear, right? So I need an x to the first power to appear. The most basic linear function, y equals mx plus b, right? That's kind of that format. So I needed something as some number times x plus a constant, perhaps. All right, so I'm going to call this, since I already have an a, I'm going to do bx plus ac. That's linear on the top, right? This is quadratic. This is linear. This is 1 less than linear is constant. Process is now still the same thing. Multiply everything by the LCD. Many things will cancel out. All of that goes, all of that goes. X minus 2 goes away. X squared plus 2x plus 4 goes away. All right, so on the left side, everything went away, so the only thing left in the numerator is 1. Over here, a gets multiplied throughout the x squared plus 2x plus 4. So that'll give us 8x squared plus 2ax's plus 4a's. And now we've got bx plus c. Watch out, this is this entire numerator multiplied to x minus 2, not just the c. So you need to put like parentheses around that. So a binomial times a binomial has to be FOILed out first. Bx times x, bx squared. Outer would be the negative 2 times the bx, so negative 2bx's. Inner would be cx. And last would be c times negative 2, negative 2c. All right, so next, equate our coefficients. X squared is the highest one in here, right? So x squares. No x squares on the left. That's 0. On the right, we have ax squares, so a of them. Bx squares, so just a plus b is 0. So a and b have to be opposites, right? X to the first. No x to the first on the left. On the right, 2a's minus 2b's plus 1c, right? Those all are x to the first. X to the zeros are your constants. We do have a constant of 1 is equal to all no x variables. You have 4a's minus 2c's. All right, so for this one to solve by hand, it can be done, lots of substitution. That can be like prettiest. So what I would do, since it's already one variable is not solved directly, and to use back substitution to keep solving by hand, I would write it as an augmented matrix. Left side are all my variables, a, b, and c all aligned, they already are, right? So I have a 1, a 2, a 4. B's, I have 1, is that negative 2? Yeah, that didn't come out too dark. A 1, a negative 2, and then a 0. And then we have 0, 1, and negative 2. And our constants on the right side, 0, 0, 1. I'd put that in the calculator. So just a refresher. Go to the matrix menu. Going to edit a matrix. This matrix is 3 rows by 4 columns. Put in these entries, 1, 1, 0, 0. Two, negative 2, 1, 0, 4, 0, negative 2, and 1. On a blank screen, go back to the matrix menu, do some math on that. We're going to do RREF, option A, I believe. Yep, option B, RREF. one matrix A, recall the matrix name, go back to matrix menu, choose it, number one, enter. Yeah, I've got a bunch of ugly decimals I don't like. So I'm going to change these to fractions. Math, number one, enter. And there are my fractions. A is 1/12. B should be -1/12. And C is, I forgot what C was, -1/3. So now I rewrite as 1 over x cubed minus 1 is equal to two fractions, where this was our A, 1/12 over the x minus 2, plus our B, bx plus c, right? So -1/12 times x plus our c plus a -1/3 is -1/3. All over that x squared plus 2x plus 4. You can leave it like that. You don't have to worry about it since it's complex fractions. That's fine. There's still two fractions added together would result in that one. X cubed. Oh yeah, there's a typo on this presentation. There's x cubed minus 8. That's right. So really, even on the test, you don't even have to go back and rewrite it for me. As long as you identify what your A, B, and C's are, that's fine. Okay. That's the whole goal. I mean, all right, case 4. You should be able to do case 4 now, almost on your own. Or at least get it set up. Q contains a repeated, irreducible quadratic factor. So almost like a combination of case 3 with case 2. Case 2 had repeated linear, so now we got repeated quadratic. So let's say we have 2x cubed plus x squared minus x plus 4 all over x squared plus 1 all squared. All right, see if you can set this one up. It's already factored for you, right? You can't factor x squared plus 1. That's a difference. I mean, that's a sum of perfect squares. There's no such factorization of that. But it is repeated, right? Because it's to the power of 2. So I'm going to pause this real quick. All right, so it's already in factored form. The number of factors we have are 2. That tells me I have 2 fractions. So I take one of the factors without the power of 2. And then I take the factor with the power of the 2. Right. Quadratic, linear on top. So we're going to put ax plus b. Second one's quadratic again inside, right? Linear on top. But I don't want to use a's and b's. I want to use some different letters now. Cx plus d. All right, next up is to multiply by the LCD, which is given x squared plus 1 all squared. X squared plus 1 all squared. X squared plus 1 all squared. And we put parentheses around these numerators to ensure that it's binomial times binomial. Cancel. X squared plus 1, that would have one factor. X squared plus 1 all squared cancels. So that's it. Simplify to what we have, 2x cubed plus x squared minus x plus 4 would equal this binomial times that one. Ax times x squared. That's ax cubed. Outer, ax times 1, ax. Inner, b times x squared, bx squared. Last, b times 1, b. And then plus the cx plus d, that's all that's left. So we got a, b, c's, and d's. Equate the like coefficients. So we start off with x cubed is the highest. You don't have to always start off with x cubed. You can start off with the constants if you want. It doesn't matter. Just that's the order I go. I just go all the way down from the highest to the lowest. X cubed I have on the left 2. On the right I have a. That's it. X squares. So a is already solved. That's kind of nice. Might be easy. Not even have to put this into a matrix. We'll see. X squares I have 1. Many x squares here? B. Oh, B solved. That's nice. X to the first. -1. Over here, x to the first, ax. No bx term. We have a cx term. And constants. We've got a +4 on the left. X cubed, x to the first, x to the second, x to the 0 right here. There's no x's. So it's a b plus a d. All right, so a and b are both solved. We can solve for c right here. Don't have to go into do a matrix. That's fine. It makes it easy. Typically, when you get many variables like this, the numbers work out fairly nicely to where you don't have to do the augmented matrix. Not always, though. All right, so if a is 2, I didn't need to put an x there. I don't know why I did that. Take that x off. We shouldn't have x's in there. So -1 is equal to a 2 plus a c. Subtract off 2, c is -3. B is a 1. So 4 is equal to 1 plus d. So d is equal to 3. So we got a, b, c, and d solved. So we can rewrite it, replacing the coefficients. So 2x cubed plus x squared minus x plus 4 all over that x squared plus 1 all squared is equal to, this was x squared plus 1, and that was the ax plus the b, so a times x plus the b plus 1. And then over here, this one was the x squared plus 1 all squared, and this was cx plus d, so -3x plus 3. That's it. So again, I showed you all 4 scenarios. However, you're doing the same process on every one of those 4 scenarios, right? So you don't have to memorize, oh, this one has this, this, and this. Just look and see how many factors you have. That tells you the number of fractions to make. Find your least common denominator. It's shown there, right? So each one of those fractions will have one of those factors as their denominator. All right, any questions? So we'll need another example. We did for the same type of problem in a sense. All good? All right. That is 11.